Welcome to today's class. Our topic today is Zener diode regulator. Now, what is a regulator? A regulator maintains an almost constant output voltage, even though the DC supply voltage and the load current may vary over a wide range. The regulator keeps the output voltage constant, irrespective of fluctuations in the input supply voltage or variations in the load current. So in today's class, we are going to see how the Zener diode regulator operates. But basically, we'll be looking at a simple Zener diode circuit, and then we'll be deriving expressions for the maximum Zener current and then solving an example. So let us dive into the topic fully. So that's the simple Zener diode circuit. For the Zener diode voltage regulator circuit shown here, derive the expression for the maximum Zener current in terms of voltage and current only. So we are deriving the expression for the maximum Zener current in terms of voltage and current only. So to begin, let us see the current flowing through various elements in the circuit. So we have current, the input current, the Zener current, and the load current. Ri is equal to Vs minus Vz all over Ii. And that's equal to Vs minus Vz all over Iz plus Il. Of course, the input current, according to Kirchhoff's current law, will divide at this node to give you Iz and Il. Now, if we solve for the diode current, we are going to have Iz as being equal to Vs minus Vz over Ri minus Il. So this expression here will enable us to get the value of the Zener current in this simple circuit. However, we are asked to derive expression for the maximum Zener current in terms of voltage and current only. To operate properly, the power dissipation in the diode must not exceed its rated value, and it must operate in the breakdown region. There are two conditions for this to occur. So let's take note of the conditions. 1. The diode current is minimum when the source voltage is minimum and the load current is maximum. The second condition is that the diode current is maximum when the source voltage is maximum and the load current is minimum. The Zener current is maximum when the source voltage is maximum and the load current is minimum. So these two conditions that we just mentioned are the conditions that must exist for the diode to operate properly, for it not to exceed its rated value. Now, using these conditions, we want to put these conditions into the equation that we derived earlier on, which is this equation here. So let us put in these conditions 1 and 2 into this equation. So that's going to give us Ri. That will give us Ri equal to Vs minimum minus Vz all over Iz minimum plus Il maximum. So that is putting in condition 1 into our first equation. Let's call this equation 1a. So if we put in condition 2 into the equation, we are going to have Ri is equal to Vs maximum minus Vz all over Iz maximum plus Il minimum. Let's call this equation 1b. If we equate equation 1a and 1b, we are going to have Vs minimum minus Vz into Iz maximum plus Il minimum, which should be equal to Vs maximum minus Vz into Iz minimum plus Il maximum. Solving for maximum Zener current, we are going to have Iz maximum will be equal to Vs maximum minus Vz into Iz minimum plus IL maximum. minus IL minimum into Vs minimum minus Vz, all over Vs minimum minus Vz. So we just derived the expression for the maximum Zener current in terms of voltage and current only. And the expression is Iz maximum is equal to Vs maximum minus Vz into Iz minimum plus IL maximum minus IL minimum into Vs minimum minus Vz, all over Vs minimum minus Vz. So that's the expression for the maximum Zener current in terms of voltage and current only. Now let us see how we can use this to solve a real problem. Now let us consider a typical example. Design a voltage regulator circuit similar to the one above to power a car radio at VL is equal to 8 volts from an automobile battery whose voltage may vary between 11 volts and 14 volts. The current in the radio will vary between 0, that is off, and 100 milliamp, it's full volume. The minimum Zener current is 1/10 the maximum Zener current. So we're simply going to use the formula we derived earlier on in solving this problem. So let's begin. The maximum Zener current is giving us Vs mean minus Vz into Iz mean plus IL mass minus IL mean into Vs mean minus Vz all over Vs mean minus Vz. Now substituting the values, respective values, we are going to have Iz mass will be equal to 14 minus 8 into 0.1 Iz mass. Of course, the Iz mean is 1/10 of Iz mass, 100 milliamp, which is the maximum load current, minus IL mean is 0, minimum Zener current. So the whole of this gives you 0 all over 11, which is Vs mean minus 8, the Zener voltage. So that will give us 3 Iz mass is equal to 6 into 0.1 Iz mass plus 100 milliamp, plus which should be equal to 0.6 Iz mass plus 600 milli. That will give 2.4 Iz mass to be equal to 600 milliamp. So Iz mass will be equal to 600 milli all over 2.4. That will give us 250 milliamp. The maximum power dissipated in the Zener diode is giving us Pz mass is equal to Iz mass times Vz, which should be equal to 250 milliamp times 8. That will be 2000 milliwatts or 2 watts. The current limiting resistor is giving us Ri is equal to Vs mass minus Vz all over Iz mass plus IL mean, which is equal to 14 minus 8 all over 250 milli plus 0. That will give us 24 ohms. The maximum power dissipated in the resistor is giving us Pri mass, which is Vs mass minus Vz all square divided by Ri, which will be equal to 14 minus 8 all square divided by 24. That will be equal to 1.5 watts. The minimum Zener current Iz mean is giving us Vs mean minus Vz all over Ri minus IL mass. That will be equal to 11 minus 8 all over 24 minus 100 milliamp. It should be equal to 25 milliamp. So now that we have all the parameters, we can now design the circuit. So this is the circuit design. So we have designed a voltage regulator circuit that is supplying just 8 volts to the car stereo, irrespective of the voltage fluctuation of the car battery or the load from the car stereo. The voltage supplied to it must be 8 volts. So that's the circuit design. So you see the importance of a voltage regulator to maintain an almost constant output voltage, even though the DC supply voltage and the load current may vary over a wide range. So in today's class, we looked at Zener diode regulator, and we said a regulator maintains an almost constant output voltage, even though the DC supply voltage and the load current may vary over a wide range. We looked at this simple Zener circuit, and they would derive expressions for the maximum Zener current in terms of voltage and current only. The expression we got was Iz mass is equal to Vs mass minus Vz into Iz mean plus Il mass minus Il mean into Vs mean minus Vz all over Vs mean minus Vz. So that's the equation, the expression that we got for the maximum Zener current. So we went further to look at a typical example. To design a voltage regulator circuit similar to the one above to power a car radio at VL is equal to 8 volts from an automobile battery whose voltage may vary between 11 volts and 14 volts. The current in the radio will vary between 0, which is off, and 100 milliamp, which is full volume. And then the minimum Zener current is 1/10 the maximum Zener current. So we just recall the expression we've derived earlier on for the maximum Zener current, and then we substitute our values and we solved for the various parameters. We solved for Iz mass, for Pz mass, and then the current limiting resistor Ri, and then the power dissipated in the current limiting resistor. I will also solve for Iz mean, and that's the circuit that we design as shown here. So that's all for today's class. See you in our next class.